All right, so we need to define the term enthalpy. Enthalpy is very closely related to Q and H, or heat, but we'll talk about the minute differences between those two. Enthalpy relates to the fact that the heat present in different substances or different amount of the substances varies. So like there's more heat in 100 grams of water than there is 50 grams of water. Or there's more heat in 100 grams of water than there is 100 grams of lead. So we call that heat content, the thermal energy content of a specific system or a specific substance, it's enthalpy. The like textbook definition you want to be familiar with is that enthalpy is the total heat content of a system at constant pressure. All right, that is important for us. We will not deal with situations where pressure changes. Another challenge to enthalpy is that we can't measure it directly. We can only measure it through changes in heat. So the change between the products and reactants, or the end and beginning of a change in a system. All right, so your enthalpy is referred to as delta H, and it's the change in the heat of the products minus the heat of the reactants. All right, so what's the difference between the heat of the products and the heats of the reactants, or your final heat of whatever substance you're working with minus the original heat, the initial heat? All right, this is where the fact that we are always going to deal with constant pressure comes in handy. Because we are not going to allow pressure to change, we can also say that delta H is equal to Q. All right, so we can also use that delta H equals mc delta T equation. That's going to make some of the calculations familiar and simple. So, for example, a 10-gram gold coin is heated from 25 degrees Celsius to 50 degrees Celsius. C, specific heat of gold, is 0.13 joules per gram degree Celsius. So what is the delta H? This is where you can use that equation we've already dealt with. All right, so our mass is the 10 grams. Our C is given to us, and our delta T, all right, remember that's TF minus TI, or final minus initial. So our final temperature is going to be 50, our initial temperature is going to be 25, so that delta T is equal to positive 25. All right, signs are important there. So our delta H is going to be equal to 10 times 0.13 times 25. Which is equal to 32.5 joules. All right, we've dealt with this equation before. We are just able to apply it to a new situation, solving for enthalpy. So something to think about is the sign on delta H. That is going to tell you if a reaction is endothermic or exothermic. So let's think our way through this based on what we already know. We've already defined exothermic changes or processes as when heat is blank by the system. All right, what is that term? We always define this in terms of the system. Exo sounds like exit. All right, so heat is given off by the system. All right. So that means the temperature of our system, if it's giving heat away, the temperature of our system is going to decrease. All right? So if you think about it, when you calculate that delta T, you're going to have something where like you're going from 50 to 25. So you're going to have 25 minus 50, or a negative 25. All right? So your delta H, when it's exothermic, is actually going to be negative. It'll be less than 0. All right? So delta H is negative when you're dealing with an exothermic reaction. Endothermic, on the other hand, is the exact opposite. All right? So endo kind of sounds like in. Heat is absorbed by the system, which means as it takes that heat in, the temperature is going to increase. All right? So that's where like our delta T, we're going from 25 to 50. All right, so 50 minus 25 is positive 25, momentary hiccup here, which means our delta H will be positive or greater than 0. All right, this is a really, really important relationship to write down. Exothermic, you get a negative delta H. Endothermic, you get a positive delta H. All right, remember that, because you are going to definitely be asked questions where, like, all you are given is the delta H, and you're going to have to be able to tell me, is it exothermic or endothermic? No, all you got to do is look at the sign. 25. Another thing I want to introduce now, but we will deal with in more detail in the future, is latent heat. All right, so not all enthalpy changes are associated with a temperature change. All right, we've dealt with that so far just because it's so easy to wrap your head around, but there are enthalpy changes in the thermal energy, the kinetic energy of the molecules that don't actually cause an increase in temperature or a decrease in temperature. The temperature stays the same. The common example of this is a state change. All right, so when something goes from solid to liquid, liquid to gas, gas to liquid, there is, while the molecules are separating from each other, their intermolecular forces are weakening, there's no change in temperature, but the molecules are still gaining energy because they're able to move around more. All right, so the heat continues to increase, the energy, without it affecting the temperature. All right, so when we have to deal with this, you're going to have things like the heat of fusion, which is this will be a constant for different substances, but it's the amount of energy needed to melt or freeze a substance. All right, and again, your sign is going to depend on if you are increasing the energy of the molecules, then you'll have positive delta H. Or if, say you are freezing water, so you're removing the energy from the molecules, then you'd have a negative delta H. All right, sub F. So for now, we're not going to do any calculations related to this. We will in the future. Just know that this idea of latent heat, it's an enthalpy change that isn't associated with a temperature change. All right, and then there's two important ones that we are going to use related to melting and freezing. We call that the heat of fusion. And then vaporizing and condensing, we call that the heat of vaporization. So this is another thing you will see related to these enthalpy changes. All right, and looking at a graph like this, you should be able to tell me if the enthalpy is increasing or decreasing, which then means you can figure out if it's positive or negative, and then that also means you can figure out if it's exo or endothermic. All right, so just looking at the graph, all right, here we have the heat of our reactants. All right, it's way up here. Let's call this 100. And here we have the heat of our products. Let's call this 30. All right, so what is happening? Is this system gaining or losing energy? All right, the heat H goes down, so this is losing energy. All right, you can also think of it as if you took 30 minus 100, your final minus your initial, you'd get negative 70 for your change in H. So this is an exothermic example. All right, so that's how you read these things. You can see, again, over here, here's your reactants. This time we've got the reverse situation. Reactants were at 30, products are at 100. All right, so our delta H, our final minus initial, would be 100 minus 30. I'm just making these numbers up so that I can do something with them. All right. You can use any numbers you want as long as you follow what's going on with your graph. Your reactants in this case should be lower than your products. All right. This is going to give me a delta H that is positive 70. You can also see that through this process, the products have more energy than the reactants did. So this is an endo. They absorbed the energy.